All right, so for our final topic today, we have Jack Jeffries from the University of Nebraska, and he will tell us about singularities in commutative algebra and simplicity.
I'd like to start by thanking the organizers for the opportunity to speak in this conference, and especially to thank Karen for the occasion to have this conference. This is all right here. What I'm going to, or my plan for this talk is a little bit strange. It's something in between a survey talk and an actual research talk. So my general where I'm going in this talk is first I want to revisit a couple of Karen's fundamental results on this topic, and in doing so, I'm basically going to take two of Mel's slides and make a talk out of it, and then I'm going to go from there and talk about some of the developments that have come from that. So results that were inspired by these results of Karen. Some that I've worked on and some that other people have worked on in recent years. So as this is halfway between a research talk and a survey talk, and not entirely a survey talk, I'm going to also start by apologizing to all the people whose results belong in this talk and didn't quite make it in. So I'm sorry about that. But I guess I don't have to apologize to Karen because I'll talk about some of yours. Actually, I do, because I'm not going to talk about all of the results that of Karen's results that are relevant to this because we only have an hour, and I heard that in the poster session there is going to be wine, so I'm going to take it. So good. So I wanted to follow also some of the things that Kevin said, Karen's advice for giving a good talk. One of them we can already check off. So the results that I want you to remember have been stated in the negative 275th minute of this talk. Think by now. And then the other piece of advice that I want to follow is, okay, what does this mean for the polynomial ring? Okay. So let me start by talking about differential operators on polynomial rings. Okay, polynomial ring with complex numbers. The ring of differential operators over this is probably what you guess it is, even if you haven't seen it before. Or at least similar to what your guess is. Involves some derivatives. So in talking about xi as a differential operator, there's an abusive notation. This is the multiplication by xi operator. So xi by abusive notation is multiplied by xi map from s to s, and I will use the same name for both things. Sorry about that. Standard notation. Okay, this partial I is the partial derivative by xi. So this is definitely a ring. Defined to be a ring generated by some stuff. It's a non-commutative ring because multiplying and then taking derivatives do not commute with each other. And the other basic thing that I want to note about this is that S is a left-D module tautologically. These are defined to be a bunch of things that are taking around things in S. And the action of the ring of differential operators on the polynomial ring is great for many reasons. Kevin has listed some of them. Eamon's listed some of them also. I'm gonna list them. So one place where this ring of differential operators plays a big role is in Weil's book on the classical groups. Where this is called the Weil algebra. This does a lot of great work in invariant theory when you can use identities and induction on degree to show that certain invariant rings are what you think they are. And there are also more sophisticated applications than this. Wanted to have something pretty classical to get us warmed up. Kevin also told us about this, reminded us about this, symbolic powers. Let me just say out loud that one can characterize the symbolic powers of prime ideals in this ring by asking, okay, what things are sent back into that prime ideal by all operators of a certain order? One stunning collection of applications of this action, of the action of differential operators on polynomial rings, came to us from work of Besnick, who applied this action to establish great finiteness properties of local multi-modules. And I want to recall this thing that showed up in Eamon's talk, for instance, zero polynomials. So the idea is that one given an actual polynomial, there's a differential operator, well, polynomial combination with some extra dummy variable grouped together. In that dummy variable, there's another S support, don't be careful. Both of these non-zero, such that let me just say this in the easiest way to understand. You haven't seen it before. Such that when I feed any power of this into this operator, I get the smaller power, the next smaller power, perhaps with some coefficient, and that coefficient varies as a polynomial. Yeah. And let me just say out loud, instead of polynomials, the smallest monic polynomial. It shows up like here in such an equation. And as Eamon told us, this is related very closely to topological properties of the vanishing locus of F. And something that very much you could have thought that I meant by this talk was the theorems of Lesser-Smith, Verlin, Kolar, and others relating the roots of these to various irrational geometry invariants of F. That's one thing. Yes, that's not where we're going in this talk. So just say related to the multiplier ideals. At the same time, this ring just on its own, so without S, has a lot of very nice ring theoretic and module theoretic properties. not just nice, it's incredible. One that's maybe not incredible, but I'll say it anyways. This is a finitely generated algebra. All right, fine. This is also left and right Noetherian. Okay, nice, maybe not incredible. But this is a ring of finite equivalent dimension, so this acts as a non-commutative ring in ways that are similar to regular rings, regular commutative rings. And here's something that's pretty incredible, one of my favorite things about this ring. Here in Cold-Grimson's inequality, which says that every non-zero DS module has dimension. I'm not going to define dimension, but think of this as being a form of full dimension. Okay? Not vector space dimension, full dimension. At least dimension of S. So the smallest possible non-zero modules are actually pretty large. And something that I'll vaguely describe. There's also sort of classification theorem for the modules that are in the smallest bucket here. Okay, let me go back here for a second. Looks like I have barely enough space to say what I need to say about this. All of these things here are refined versions of the facts, the idea that one can use differential operators to undo multiplication on S, to make degrees of elements smaller, bring big elements back to closer to 1. Here, this comes out very explicitly, right? I'm taking powers down. I guess here, I said out loud, this is about some sort of induction on degree, and not hard to convince yourself that these are variations on the same idea. So one thing that collects that idea is that as a left DS module, S is simple. I can get from any element back to 1. Something kind of related to this, that's also kind of related to this, something that we heard about in Mel's talk. One good ring theoretic property that's the ones on this list, and sounds like something over there. This ring is a simple ring, which means no non-zero proper ideas, two-sided ideas. Okay. So these are some good things about this ring in the polynomial case. Let's see where we head next. Singularities, yeah. kind of hate to do this because if you haven't seen the definition before, you're not going to get anything out of it, but I still feel like I have to do it anyways. And so given a pair of commutative rings, commutative ring and subring, let's say, let's start the same way that we started in S. With the multiplication maps. And the idea is that every time y increases, we get a little bit less and less commutative. It should at least be alinear. And my failure of commutativity was one of the things on the previous list. All R and all, maybe it's just D0. And when we put all these things together, this again forms a noncommutative ring, or a possibly noncommutative ring. And again, R is tautologically left modulo it. So maybe I'll just say out loud that if we plugged in C and the polynomial ring over C, we would get the same thing that we were looking at before. And now maybe looking at this definition, we might be tempted to think that looks hard to compute. Let me start with the best case scenario. Not polynomial rings, that's where we did that. And next best case scenario, at least in my book. Very well studied setting. When R is a ring of invariance of some group action. So I'm going to combine intervals here. So I'm going to bring over C and G of group acting on S. When G is finite and a little bit of fine prime with zero reflections, ignore that if you like. Then we have a good way of understanding this. G is also going to act on ds by conjugation, and the differential operators on the invariant ring are the invariant differential operators. And for many infinite group actions, something similar is true. This rejection. Let me make at least a couple of cases this way. Particularly, this is true for toric rings. And since I was going to be precise, given a normal affine semi-group ring over C, you can realize it as an invariant ring in such a way that this is true. Abbreviations. Generic determinantal rings, alternating generic determinantal rings, symmetric determinantal rings. These can all be written as invariant rings, such a way that this is true. Yes, and there's descriptive letters on the side. And not to mention Jerry Schwartz's was some of the most comprehensive results in this direction. All right,
Here's A is C, right?
oh yeah, good point. Let me just say out loud.
Or is A Z? That's my question.
C. A to C. Yeah. I'm going to write the C's over. Okay, they'll just say out loud when it happens. All right.
It's an algebra over a field that's naturally to suppress that notation.
Yeah, good. I've gotten permission already. All right, so that was pretty good. Now let's look at a. Here's a pretty tame looking ring. It's a famous example. It's a Bernstein Gelfand and Gelfand that sort of everything goes wrong already for this innocuous looking example. This is no longer a finitely generated C algebra. This is neither left or right Noetherian. And the thing that I think is even worse. This is naturally graded, and but as such, there are no elements of negative degree. All right.
So you can't lower degrees.
So we can't lower degrees. This is ominous for things that we've seen before. Okay, so let's put ourselves in a situation of commutative algebras over OK, commutative Noetherian, and dr is always dr OK. Let's remember the definition of this one. It's been a few hours. Say R is B-simple if R is a simple GR module. This is something we admired about the polynomial ring. And waste no time in saying it. This example, BGG example. This is not D simple. The ideal, the homogeneous maximal ideal is stable under the action of differential operators because I'm never going to take something positive degree to degree 0. Let's see. This comes from a thesis that Karen advised, the first one. Not in the general statement of the paper, but picking up the objects from Star's talk. Let's take a square root monomial ideal. Then the DR submodules of R are exactly the intersections or sums of minimal primes. And since I'm allowing myself to take a sum of one thing and an intersection of one thing, then there's always at least something interesting if I have an interesting square root monomial. These are never D simple unless these were polynomials. All right. I'm going to combine two things from the results from the parents here. Mel didn't tell us this one yet. Take a direct sum of the polynomial ring. That's D simple. And that should be partially finite reduced. Then the positive characteristic we get n and R is D simple. Unfortunately, that's not isolated here, but at least this is very closely related to strongly related. Okay. So maybe I should say even if R is normal, one can find examples that are D simple but not exponent here. So this is as good as we're going to get in terms of separating pieces here. This theorem in both parts really tells us something strong about the thing that got erased, the title of the talk. The simplicity is reflecting in a very nice way in this theorem, the singularities theorem. And I have to think of this as a type of singularities. One other thing I want to note about this is that this is the only one that talks about characteristic 0 between these two things, and this condition, the hypothesis, we are asking a lot here. This is a very strong thing to say, to demand of knowing more. All right. So,
So it's D-simplicity.
Sorry?
So it's D-simplicity.
And so is D-simplicity. It's one of my favorite ones. Yeah. So I want to say a little bit about the aftermath of this thing. So the study of D-simplicity continues. It's still something that I think that we would like to understand better. In particular, the relationship between D-simplicity and singularities and characteristic 0. There's something that one could hope for here. So direct sums of polynomial rings are, under my hypotheses, of strong F regular type. One could hope that that's enough to guarantee D-simplicity, and definitely came up with an example where this is not the case. Looks similar to something else, except this extra variable in the same degree. Right now means that we've got a negative A here, and in fact, this is tail T. Not be simple because there are no operators in negative degree. So the link between D-simplicity and Kevin's diagram is a bit more subtle in characteristics here. Along similar lines of, or somewhat similar lines. There's another very nice recent example due to Alton and Karen Smith. It says that we should be careful if we're in the way that we're thinking about the word singularities. One also needs some sort of finiteness hypotheses to get started with these games. So there are one-dimensional regular C algebras. That are not D-simple, so one needs some sort of finiteness hypothesis. So before we go on to another, the other theorem that Mel threw us into, I want to just briefly mention some results that are not directly about D-simplicity, but are very much inspired by Karen's results and techniques. So one of the things that that we have listed on this same board, which I could just slide, that was in the spirit of D-simplicity, a sharpening of D-simplicity, was existence of emergency set polynomials. The partial direct sum and the polynomial when the characteristic is 0, and the polynomial when the field characteristic is 0. Then every non-zero element has a Bernstein state of polynomial, meaning that there exists a non-zero functional equation. And the idea behind this proof, I think in my understanding of it, is very much inspired by Aaron's proof of part 1 here, which is basically a recipe to take differential operators on S and bring them down to differential operators on R. Here they develop a theory of differential direct summons, which is like in my mind, a sophisticated ratcheting up of this sort of idea. And with Luis and Damon, we also had a characteristic P version of this that I think is also somewhat inspired by this theorem here. As Damon told us, it's not Bernstein state of polynomials. There's something more subtle, a more subtle object here. But we say there's a characteristic P analog for nice singularities. So again, for direct sums of polynomial rings. We're really just graded with RP. And there's much more to be said about D simplicity, but I also have to talk about D as a range. No, I don't have to, but I want to. And a little bit of backstory to what comes next. There were a number of theorems in the 1980s and 1990s that showed that for many nice rings, ring of differential operators is a simple ring. So for rings of finite groups, toric rings, and the rings that Levister and Stafford studied that I mentioned before. Generic alternating symmetric determinantal rings. I wrote them before. Levister and Stafford. Here is a simple ring, and they Levister and Stafford.
These are over C.
This is over C, yeah, thanks. Yeah. That's important. Should have kept the subscript. There's a question / conjecture of Levister, Stafford, and Schwartz that small invariant rings of linearly reductive groups over C. We can get that for all groups as a simple ring, and you can see a lot of evidence in right above. I should note. But this is a stronger property. If DR is a simple ring, then R is a simple D module. And with that in mind, we've already seen more evidence for this conjecture, which is that in this setting, this linearly reductive condition is enough to ensure that R is a direct summand of a polynomial ring. And we know that at least R is D simple from here. And I'll state this slightly differently, so it looks like it's something we haven't seen yet today. We take a polynomial ring over perfect field composite characteristic, and this is how one finds this in the introduction to the paper. Take a direct summand, such a polynomial ring. Then DR is a simple ring. And this is very much the characteristic P version of the conjecture. Here gives us direct summand. Characteristic 0. As Kevin mentioned before, a lot of really cool things go into this proof. Things that have very much stuck around and become interesting in their own right. So to some extent, the real hypothesis in this theorem is that R is graded strongly at regular, and has this FFRT condition that Mel mentioned in his talk. And in this proof, an analysis of what would later be rediscovered in point F signature plays a major role. And actually, maybe I'll also circle back to another interesting notion that shows up in this paper later on. Just because this came up in as a question in Mel's talk, strongly at regular does not apply FFRT. And so there are examples of Singh and Swanson that show the difference. And this theorem has also been, not that one, this one. That one too, I guess. This theorem has also been a big inspiration in my own work. I want to just briefly discuss a result that's inspired by this, and very much inspired by this, and tries to build on this conclusion here. So, stated, this is not going to be something that I know to be strictly stronger than dr is a simple thing. But this was, remember, somewhere on this board of good things, good output things. Bernstein's inequality holds for dr. Then wow, this. Every non-zero D module is extremely large. Under these hypotheses. Yes, maybe this is one of those theorems where we're really hoping for the moon, and we got that it holds for finite groups, but we'll be happy with ourselves. So
Did you read that out loud?
Oh, yes. Oh, and also erase and rewrite it because I was pretty bad. Okay. Or it's an invariant ring of a finite group.
Thank you.
Yes. And certain toric rings in characteristic 0. Okay, this is probably something characteristic 2.
So for the second one, you mean in any, the characteristic here is anything,
Yeah.
even the word being divisible by p?
Oh. No, let me make, there it is.
That's a dumb question.
No, what is it?
Is the dimension also bounded above by 2 times dy, like
Yeah.
in the reproducer?
Yeah, so in the case where let me at least say for like a finitely generated graded, right?
Mhm.
Yeah, and at least in that case. Of course, in under the rough wet dimension actually is here, right? So, yes, but the upper bound holds, and without any of these nice hypotheses.
Yeah, that's what I was guessing.
We've already seen, as you said to me, sorry. This is, these two are going to work with Seth, and now Hernandez. And that's the width. And this last one is combines more recent work. From the recently graduated DHE students. And one of our incoming DHE students. me say just a little bit about what goes into this. Make it sound like it's more related to this theorem than perhaps it looks at first glance. So for any graded ring, graded in algebra, one has a multiplicative filtration on dr that's analogous to currency filtration on yes. And each of these,
So the Bernstein filtration on DS is not by the order.
that's right, it's not by the order, it combines order and degree. So, so partial I counts against you for 1 point, but xi also counts against you for 1 point. Yeah, thanks. And in each case, we'll show that dr is simple in a way that's compatible with this filtration. What does simple mean? It means no non-trivial proper two-sided ideals. So if I had anything in a two-sided ideal, one was in it. And my condition here is going to be that I can get back to one in a way that's not too expensive from the point of view of filtration. Let me call this condition linearly simple.
What's that say?
Linearly simple.
No, the
Oh.
definition.
Oh yeah, so one, yeah, so there exists a constant independent of your operator and where it lives in the filtration, such that I can take left-right combinations of and add them up of things that are in the C times I piece, C times I filter piece. So I only need to spend 7 times as much if I want to get back to it. But that makes sense.
I think so. It's giving you a bound on the, not exactly the order, but something like the order.
Something like the order, yeah. Something like the order, but also the degree.
Right,
Yeah.
that you can take an element to one.
And this condition implies Bernstein's inequality. And this is based on ideas from Joseph's proof of Bernstein's inequality and work of Babila. Ideas coming from. All right, so now one has to show that you can do this. And in the characteristic P case, we follow the Plato from here. So one follows the strategy. And let's say something about the short case. Whatever. Somewhere whatever. In the tort case, we also end up showing something that's related to an idea it's in paper, which is that you really just need to focus on one element. And for that matter, one element is the singular focus. So suffice it to check this linearly simple condition. Not for all delta, but for one delta of order 0, and an order 0 element that's in the singular locus.
You need to define any of this.
Yeah, defining ideal singular locus. And people are familiar with the snipping and Berkeley recognize this as being reminiscent to a condition shown there for checking d-simplicity by looking at the singular locus. There's lots more to say, but there's also wine in the poster, so maybe it's something.
Questions?
So when you were mentioning for this case result about when you have activity, as in activity d-simplicity is equivalent to stronger activity. I have a dumb question. So how about if rational?
Well, so if you're rational, then
Like do you have something?
What was the question?
Say the question.
oh yeah, so instead of at purity
No,
in
no,
the theorem about d-simplicity, if you replace that with rationality. So
no. Can you get if rational in some sense? Like always assume activity or activity something like that. Okay, instead of stronger probability, can you get if rational?
with something weaker than d-simple,
Yes.
I don't know what.
What was the question? Oh, if you,
Yeah,
on
so
the
assume-
right hand side, you have F rational plus F pure. You describe
Yeah,
something
yeah,
with
so
their
that's-
differential operators, that would be more simpler than simple.
Yes.
It's not obvious, yeah.
That's the CMOD freezing quotient of the elliptic curve. That's rational.
Right,
So I would say after rational. The one's pretty nice.
yeah.
Will you say that again? Is it Z?
If you take the elliptic curve example, there's a CMOD freezing quotient. That ends up being rational.
Sure.
But still with no operators of negative degree. So sort of the same thing that happened in Cantor's theorem is equally happening in that example as well. Yeah. So the short answer is probably.
Does the certain toric rings mean it definitely doesn't work for other ones?
No. No, yeah. It means that we've only been able to do certain toric rings so far.
Okay, which ones?
Coordinate rings of sacred products, so PA cross PV, and certain triple sacred products. So it's a not an extremely long list yet, but
Do you use it, do you do it in terms of like the cone of the?
Not-
variety?
not really. I mean,
Probably
what
cone.
we're leaning heavily on this. So take an element in the singular locus and just find your way back to one.
I see.
In this sense.
I see.
Sorry, in the
Oh, yeah,
polynomial case, I know variance inequality can be seen as a corollary of this symplectic geometry fact that singular supported D modules is coisotropic.
Yes.
In these singular cases, is there any sort of symplectic geometry known or suspected, sort of lying under the hood here?
So there is, okay, so there is an interpretation of this. So maybe the first interpretation that comes to mind, there's a natural symplectic structure around on the associated graded of the ring of differential operators. And in this case, so for invariance of finite groups and characteristic 0, that stronger version is false. Yeah, so there is something subtle happening here from that point of view. Yeah. Good question.
Maybe related to that is, you mentioned before that there were these characterizations of the smallest case polynomial modules, essentially, right? Do you have any characterizations of that smallest dimensional modules in
We don't have,
settings?
we don't have such a, yeah, we don't have such a result. Yeah, it's something we've thought about, but not really. Okay.
All right, if there's no further, one more question.
So,
One more question, two more questions, okay, right there.
So, thinking of the BGG example, so for homogeneous polynomials with isolated singularity, is there a general relation between not being simple and not having negative degree operators?
So certainly if you don't have negative degree operators, you have no chance of being simple. I don't know a counterexample for the other way. So I don't know an example where there are negative degree operators. Do you have one?
I think you take a product of a d-simple thing and a non-d-simple thing, and use the.
Oh, yeah, okay, sure.
The trivial ones.
Yeah,
I don't know an interesting one.
Yeah,
Read that, I have no knowledge, but interesting.
I don't think because that will probably run into the singularity.
Oh, yeah, that doesn't have an isolated singular.
Ah, that's true. So no,
Okay.
no, I don't know any.
I don't have a. Yes.
Yeah, so it's a very basic question because I'm not familiar with this, but I was trying to understand. So we're getting a geometrical intuition, a picture intuition of the R being simple, and yeah, do you have an idea for this? Because I guess R being simple to me, I mean, if I got it right, it means that you have your singularity, but you cannot go further, taking more quotients and getting also singularities. Like you cannot get further singularities by quotient in your ring or by going to sub-varieties of your variety.
Well, the sort of simple that this is most analogous to is, so if you just ask for R to be simple as an R module.
As a DR module.
Yeah, but just to, I don't know, just to line up with the analogy, see if I'm lining up with your analogy, right? So for R to be a simple R module, that means that it's pure.
Yeah.
So I guess I didn't understand that part of your question, right? So for the geometric picture for R.
I'm thinking that if R is a simple DR module.
Okay.
I guess that means that you can. I mean, a quotient of R is a DR module if the derivatives of your quotient is, if the Jacobian of the quotient is contained in the. No,
Well, there's also higher order operators. There's also higher order operators.
Yeah.
So one needs in general to use these higher order operators. Yeah.
They're not generated by degree one operators.
Okay.
Yeah. And in fact, if you only needed, under model conditions, if you only needed degree one operators to make R be simple, then R was a polynomial to start off with.
Super. You have.
Yeah. So it's really the higher ones that are doing any of the work.
Yeah. Okay.
Well, I wanted to ask a stupid question. You said earlier, I might have done this at some point, but I don't know who proved it or why. I think you said that if a ring has FFRT, then there's a notion of Bernstein-Segal rings?
Yes. So, and what I mean is the same notion that Eamon alluded to in his talk. So for polynomial rings and characteristic P, right, there's this theory that Musbatsa and Batoon and Eamon in the ideal case developed. And the point of the theorem that I wrote down is that theory works in the FFRT case as well.
I see.
Yeah. So one also has finitely many roots for your Bernstein-Segal polynomial, or finitely many Bernstein-Segal roots for any.
So this result is that?
So that was the singular case that was with Eamon and roots.
I see. Okay.
Any further questions? All right, if not, let's thank Jack again.